What are we doing now? Okay. Hey team, I'm Maddie. Welcome to Science Side Up. And today we are talking about the ideal gas law. The ideal gas law tells us how pressure and density and temperature all relate to each other for an ideal gas. And what is an ideal gas, you ask? Excellent question. For me, the best way to think about what an ideal gas is that it's a gas that doesn't do anything interesting. There's no attractive or repulsive force acting between the molecules. We're also going to assume that no chemistry is happening between the gas molecules. They're not gonna bind to each other to make a new molecule, nothing like that. And we're also going to assume that anytime these gas particles collide with each other, or say with the wall of their container, that it is a purely elastic collision. Fundamentally what that means is that there's no energy lost from the collision. So if, say, my ideal gas molecule collided with a wall, it would bounce off with the same speed that it hit it with, and the wall wouldn't move. Obviously, there's no real gas in nature that has all of these properties, but when we make those assumptions, we're going to be able to sort of get at these fundamental relationships between what we're interested in, between pressure, density, and temperature. If you can remember back to high school chemistry, or if you took high school chemistry, you might have seen the ideal gas law written like this. Pressure times volume is equal to number density times the ideal gas constant times temperature. Usually for atmospheric stuff, we're gonna simplify this down by dividing my volume over, and we get this. Pressure is equal to density times the gas constant times temperature. So let's say we have some cylinder and it's full of gas and it also has a plunger in it, so we're able to change the volume. Think of a bike pump. So here's our canister, it's full of gas, and there's a plunger here. Now let's say we move this plunger in. We've effectively increased the density. So if we're looking at our equation here, we made density go up from where we were previously. And I'm just gonna draw a little constant over the gas constant to remind us that that doesn't change. So we've changed the density. Now, in order for this equation to stay true, in order for this balance to still be there, what's going to happen is that either pressure has to go up or temperature has to go down. And in reality, both are going to happen. If you've ever gone paintballing or messed with a CO2 cartridge at all, you know when you fire your paintball, you kind of get a burst of cold air on your hand? Well, that's because the air in that canister is really, really dense. It's under a lot of pressure. And so without doing anything else to it, just by making a physical change by compressing the air, we actually made it really cold. Now let's think about how this principle is going to apply to the atmosphere. Let's imagine that we have a balloon and we fill this balloon with air down here at the surface. Then we take this balloon and we raise it up. Now that my balloon is high up in the atmosphere, well, what's changed? Well, we know that pressure has gone down a lot. So the pressure on the outside of the balloon is much less. What we're gonna see in response to that is the density and the temperature of the air inside the balloon is going to change. Now, we're gonna assume that our balloon here is perfect and it's not gonna leak. So the same mass is gonna stay inside the balloon. So what we would see to make density go down is we would see our balloon expand. So now we have a much bigger balloon. And we're also gonna see temperature inside the balloon drop. That should be pretty intuitive. If we think about climbing up a tall mountain, we all kind of know that it gets colder the higher up you go. And that's predominantly because of the change in pressure. The lower pressure means a lower temperature. So just by taking a balloon full of air and lifting it up into the sky, bringing it on top of the mountain with us, we've seen that the air inside the balloon is going to expand and its temperature is going to drop. This type of thought experiment is really common in atmospheric science, and it's one I'd really encourage you to get comfortable with. We usually would call this like lifting an air parcel. So if we're thinking about taking air from somewhere and moving it somewhere else, that's all these air parcel thought experiment things. Okay team, that's all I've got for you today. I hope you liked this video and I will see y'all in the next one. Bye team!